There are 9 languages you can choose from the audio track. Go to Setting and select your preferred language audio track. The link for the Chinese version is in the description. Also, you can enable auto-translate to select your preferred subtitle too. I have included the link to download the FreeCAD and STL file in the description if you want to try. At first glance, the rolls uphill, anti-gravity toy seems to challenge the very laws of physics. How could a double cone or a ball possibly roll uphill on its own? The slope of this ramp is 3.8 degrees at both sides. Put the double cone at the left-hand side, the cone rolls down. Put it at the right-hand side, the cone rolls down too. Put another double cone at the left. It rolls down too. Try the slope at the right near the top. It rolls up and falls to the hole. Put it at the right near the bottom. It still rolls up and get into the hole. I printed a plastic ball and give it a try. It goes uphill and down to the hole. But this double cone rolls down at the same slope. Try a steel ball of same diameter, it also rolls uphill. Move it near the bottom. This time, it stays. If I place it a bit near the top, it rolls up. Try the right side close to the bottom, it rolls down. Change to another ramp and the slope is 5.7 degrees. Try the first double cone, it rolls down. The second double cone will just stay at the slope. Not moving up nor rolling down. Just like this. How could a double cone or a ball possibly roll uphill against gravity? The secret lies in its design and clever manipulation of gravity. The ramp, wider at the top, creates an optical illusion of climbing upwards while the true magic lies in the shifting center of gravity. As the double cone moves forward, its center of mass actually descends, giving the impression of an impossible uphill motion. Here are the design details. First, pick a shape of the double cone. The one I use is a 90 degrees cone. Then decide the positions where the cone will touch the ramp at the top and the bottom. The width of the top line is 40 mm, and the bottom line is 16 mm. The distance between these two lines is 12 mm. Use 40 mm as the width of the ramp at the top. 16 mm for the width of the bottom. From the drawing, the vertical distance is 12 mm. That means when the double cone moves along the ramp from the bottom to the top, the center of gravity goes down 12 mm. If the increase in height from the bottom to the top is less than 12 mm, the double cone will move uphill in the perfect situation. Such as very smooth ramp, heavy solid double cone, etc. However, there is friction along the ramp. The center of gravity may not be exactly at the center, especially for a 3D printed double cone. The cone may sway along the ramp as the cone is not heavy enough. Considering all these factors, I used 8 mm, and it will be good enough to move the double cone up the slope. The top will be 8 mm higher than the bottom. The length of the ramp is arbitrary. However, if it is too long, the slope will be very small and is not obvious. Also, there will be more friction. In this example, I set the length as 120 mm. At the other side, I create the slope which is same as the uphill section, 3.8 degrees. But the width is constant along this section. So, the double cone just rolls downhill to show the contrast. Once you know the theory, you can decide the size of the ramp and work out the dimensions for the double cone. Either way is fine. When I increase the slope of the ramp to 5.7 degrees, increase in height is exactly 12 millimeters, the double cone will just stay at the slope, not moving up nor rolling down. Because the center of gravity of double cone remains at a horizontal line even it is at different positions of the slope. When I use a double cone with smaller angle like 40 degrees, the distance between the with 40 mm and 16 mm is 4.4 mm only and smaller than 8 mm. So, it rolls downhill. For rolling a ball uphill, the concept is a little bit different. With a ball of 45 mm diameter, I also position two lines with width 40 mm and 16 mm. However, I cannot just use the distance between these two lines to get the answer. The slope for the double cone is constant. But for the ball, the slope required is changing along the sphere. Let me review the data for the ramp. Width changes from 16 mm to 40 mm, height increase is 8 mm. So, for every mm increase in width, height increase by 0.33 mm. If the center of gravity of the ball drops more than 0.33 mm when the width increases by 1 mm, the ball will roll uphill. With the drawing of the ball, width increase from 17 mm to 18 mm, height drop is 0.21 mm. From 25 mm to 26 mm, the drop is 0.34 mm. That means from 26 mm width and wider, the ball should start rolling uphill. Check it at 30 mm and 31 mm position. The drop is 0.46 mm. So the drop is even more. Place it at about 28 mm width and it rolls uphill. Place the ball at about 25 mm width, it will stay there. Because of friction, center of gravity position, and the ramp is not very sturdy, I have to move the ball to about 18 mm width before it starts to roll down. Let me go to FreeCAD to create the 3D models. Create a new file. Create a new body ball. Create a new sketch. Draw a centered arc, radius 22.5 mm. Use polyline to draw the shape. Set this angle as 60 degrees. These 2 points as 12 mm. These 2 points as 4 mm. This is 2.5 mm from the origin. Make these two lines parallel. Draw straight lines to joint these points. Close the sketch. Make revolution. Switch to fastener workbench. If you don't have it, install it from the add-on manager. Select the threaded rod. Change the diameter to custom. Change the value to 7 mm. The length is 20 mm. The pitch is 1 mm. Right-click the threaded rod to get the transform tool. Use translation increment of 10 mm. Rotate the rod by 90 degrees. Move the rod by 10 mm. Change the thread to true. Change to part workbench. Select the ball, hold the control key and select the threaded rod. Apply cut. Thread is cut inside. Go to View. Change transparency to 80. You can see there is cone above the thread. If the top is flat, there may be supporting structure during 3D printing, and it is difficult to remove. With the cone shape, there will be no supporting structure required. Rename it as ball. Select it and duplicate. Hide the ball. Rename the duplicate as cone A. Open the sketch under Revolution. Change the diameter to 30 mm. Draw a straight line to joint these 2 points. Change the arc to construction line. Close the sketch. Show the body. It is the 90 degrees cone. Select cone A and make duplicate. Rename it as cone D. Open the sketch under Revolution. Delete this line. Use polyline to draw the shape. Make this angle 70 degrees. Make this line horizontal. This line is 7 millimeters. This line is 20 millimeters from the x-axis. Make these two lines parallel. This distance should be 25 millimeters instead. Close the sketch and I get another cone. Switch to fastener workbench. Add a threaded rod. Diameter 6 millimeters, pitch 1 millimeter. Change the length to 16 millimeters. The threaded hole is 7 millimeters diameter, so I use a smaller threaded rod. Change thread to true. Hide the cone. Select the threaded rod. Export is as STL file. Select the ball, export to STL file. Same for other two cones. Switch back to part design. Create a new body, name it as ramp. Create a new sketch on XY plane. Use polyline to draw the shape. Select these 2-point and x-axis. Apply symmetric. Also select these 2-point and x-axis. Apply symmetric. Make this line 40 millimeters. And this one is 16 millimeters. This section is 70 millimeters. This section is 120 millimeters long. Extrude. Select the ramp as active body. Length 38 mm. Create a new sketch on XZ plane. Get external geometry of these two lines. Use polyline to draw the shape. View section. This point is 30 mm from the x-axis. Select these 2 points and the y-axis. Apply symmetric. Set horizontal distance as 10 mm. Vertical distance is 20 mm. Select these 2 points and y-axis. Apply symmetric. Cut the shape. Select Through All. Symmetric to plane. Select these 4 surfaces. Use Thickness tool. Check Intersection. Uncheck Make thickness inwards, so the inside dimensions remain as the sketch. Change joint type to Intersection. Use 3 mm for thickness. Select these 2 edges, apply chamfer. Two millimeters. Select these 2 edges, apply chamfer. Size is 1.99 mm. If I use 2 mm here, there will be problem in matching the chamfer at the other edge. Create a new sketch. Select XZ plane. Get external geometry. Draw a circle, 20 mm diameter. Get external geometry. Set the distance as 12 mm. Cut the shape. Select Through All. Symmetric to plane. Select the body, export as STL file. All the parts are completed and I can print the 3D models. For this toy 10% infill is good enough. Remove the supporting structure of the screw and assembly the ball. The threaded hole is nice and clean, no supporting structure. Please subscribe and give it a like. Thank you for watching.